So I'm Ron. I'm a software engineer at NVIDIA, working on AI infrastructure. Before NVIDIA, I worked at Google for quite a number of years.
My name is Richard Whitcomb. I'm a software engineer also working at NVIDIA on Rapids, and previously I was at Spotify and Twitter doing similar things with Spark and the whole Hadoop ecosystem.
Cool. Yeah, so contrary to popular belief, NVIDIA actually does have a lot of software engineers. In fact, we might actually have more software engineers than chip designers. So I guess before we dive in, probably a lot of people are asking, like, why do you want to run Spark on GPUs? I guess if you went to yesterday's keynote by David Patterson, Turing Award winner, you know, like, Moore's law is dead, right? If you look at sort of a single thread performance, it was going, it was doubling every, one and a half year, 18 months, 2 years for, quite a few years, and then in the last almost 10 years, right, it's actually been pretty flat. So single thread performance hasn't really improved that much in the last decade. So that's kind of the compute power you have on one hand, but on the other hand, if you're working on Spark, if you're working on big data, your data is sort of also following some kind of Moore's law, right? You're probably doubling every 2 years, and that's not slowing down at all, right? So you sort of have this, conundrum. You don't have more compute, but you have more data, and you want to actually get more intelligence out of your data. What's the solution, right? So as Patterson said, really you need application-specific accelerators. When you look at GPU, really that's the original accelerator, right? If you look at the sort of GPU performance, started in like early 2000s, it's been kind of doubling every 18 months, 2 years. That trend is still kind of holding up. Hopefully, in the next 5-10 years, we'll still see this kind of doubling. So by the middle of by 2025, the GPU might be hundreds of thousands of times faster than kind of a single thread CPU. So we have a lot of potential to kind of leverage GPU to accelerate your data workload. So how do we do that? So if you look at kind of a typical, this is I think it's a Turing GPU kind of diagram, right? A GPU typically has 2,000, 5,000 cores, right? It's very massively parallel. And if you look at this diagram, there's these things we call stream multiprocessors. There are typically several dozens of them, and each SM has multiple execution engines. You can launch typically maybe like 64 threads on each unit, and they can all run in parallel. So it's a very massively parallel execution system, and it has its own L1, L2 cache, has its own memory controller, shared memory, global memory. So it's kind of a very complete sort of parallel computing system. So one of the kind of maybe a point we have to pay attention to is at the top, there's it's connected to your rest of your system through a PCI Express bus. And that's not, it's for peripherals, it's not like super high bandwidth latency, sometimes it's bad. So that's something we need to watch out for as we go through the talk. All right, so in this talk, we mainly want to tell you a story about kind of a user's journey. When you talk to our customers, and most of you probably are facing the same problem, right? You have a lot of data, you want to kind of train machine learning models to help you with your business, right? No matter what industry you're in, no matter whether you're a software engineer, a data engineer, data scientist, you all face very similar problems. So we kind of want to show you a journey we took. Maybe it's not a real business problem, but maybe it's very representative of the type of problem you run into. So we used some mortgage loan performance data from Fannie Mae. We want to kind of predict, are you going to be late for your payment or not for each loan? So we use XGBoost as a machine learning library. Of course, it runs on Spark. And our kind of main interest is to see how can you actually accelerate your workload on NVIDIA GPUs. All right. So a little bit about the data set. It's, like I said, it's from Fannie Mae. It's actually a public data set. You can download, go to their website and download. So it's 18 years accumulated, about like 39 million loans. I guess each month when you have a payment, they collect sort of the performance record. So in total, it's over 2 billion records on the performance of the loans. The raw data is like CSV text file is 168 gig. It's not too big, but it's not kind of trivial either, right? It's kind of like a good example to work on. So XGBoost is a pretty popular machine learning library. I think at one point, like maybe 80% of the Kaggle competitions was won using XGBoost as a machine learning library. So it uses gradient boosting to build decision trees. It's used pretty widely in the industry. It has this integration with Spark for a while now, so you can actually just run it on Spark. You get kind of automatic distributed training leveraging Spark. Probably a lot of people don't know we actually have GPU support in XGBoost for a while, so you can actually train the XGBoost model on a single GPU for, I think, for a couple of years now. And more recently, we added sort of multi-GPU support. If you have like 4 or 8 GPUs on a single machine, you can leverage all of the GPUs. This is using a library called Nico. It's a sort of a collective communication library from NVIDIA, similar to things like MPI, but it runs on GPU. And then even more recently, I think in just the last 3 months, we added sort of multi-node support. In addition to training on multiple GPU on a single machine, you can actually train on multiple machines with multiple GPUs. And then kind of to combine all this thing together, now we actually have some support. You can actually run Spark on multiple node, multi-GPUs. So you kind of just put everything together. So for this sort of example, we set up a standalone cluster on Google Cloud. Mainly, it's standard cluster mainly because we want to have GPU added, so you have more control over it. But in theory, you can use Yarn or Kubernetes or anything that's supported by Spark. So for this particular experiment, we used 5 virtual machines on GCP. They're pretty beefy machines. Each one has like 64 cores, like over 400 gig memory, typical hard disk and networking. So in addition to the CPU and memory, we actually have added the Tesla T4 GPUs. These are the Turing GPUs. That's kind of the latest generation. They're actually fairly cheap. I think on GCP, it's about the same price as sort of the CPU VM. So by adding the GPU, you sort of double the price of your VM. And we can see like what benefit you can get from that kind of cost increase. So for this particular experiment, we run 4 Spark workers each VM, so they can each worker can take advantage of a T4 GPU. Right, so once we have everything set up, right, so your work is actually pretty simple, right? So this is kind of your typical Scala code for training an XGBoost model, and you set up parameters, you load your data, you set your feature columns and label columns, and then you can just train it. Right, so only difference is this highlight line. So instead of using a sort of CPU-only tree method, you switch to a kind of a tree method that's supported by GPU. It's called a GPU histogram method. So that's really the only change you need to make to your, if you have existing XGBoost code running on Spark, that's really the only thing you need to change. So what do we get from this? So we did some kind of initial benchmarking, right? It's kind of hard to measure everything because if you're running in a distributed system, there's a lot of moving parts. There's data movement, there's reading from disk. So it's kind of hard to quantify very accurately what speedup you can get. So the best thing we could do is actually you can just time the training loop, right? Because that's where you spend most of the time So this is literally just a kind of a for loop in the XGBoost Spark code. It's a for loop in Java. So we measured like with the GPU turned off, you just run it on CPU, versus you turn on the GPU using the GPU histogram method. You can see you actually see a pretty big speed up, right? Like it's 6-7x speed up just by turning, just makes that single one-line change. So when you train a model, this is, if you're on CPU, it takes maybe 17, 18 minutes. Switching to GPU, it takes only like a couple of minutes. So it's a fairly significant speed up without too much effort on your part. So it looks a pretty promising result, but then we look at the whole machine learning workflow, right? If you're working on machine learning, you probably know training models and doing prediction. That's probably just a small portion of your whole work. You have to kind of read data from, in this case, from CSV. You have to transform the data. You have to do like convert strings to floating points. You have to kind of assemble the vectors. All these things together, the rest of it is actually fairly slow because you're now leveraging GPUs. So how do we solve that problem so you can actually have faster end-to-end sort of machine learning workflow? I just hand off to Rich to talk more about that.
Yep, thanks, Ron. So the question is, how do you speed up? So before we're talking about XGBoost now, but now we'll start to talk about ETL jobs. And what does it mean to speed up an ETL job on the GPU? And ETL jobs have things like joins, group bys, aggregation. So it's a very different workflow than you kind of expect from like a TensorFlow, PyTorch, or XGBoost style job. And one thing too is you can't just kind of take normal Spark and just kind of throw it to the GPU. Because if you remember the GPU image before, everything's kind of like there's many, many cores, so you kind of want to parallelize all your processing. And row-based data, it doesn't really fit into that model. There's no really way to put one row into each core. Like, you're not gonna get any speed up, and it's gonna actually slow down the job dramatically. So the first step before you're able to do any type of processing on a GPU is you kind of have to switch the way that Spark operates to go from row-based data to column-based data. So what I'm gonna talk about here is kind of some of the journey we've taken, I guess it's over the past year almost now, to go from starting to think about how do you do these ETL jobs on a GPU to where you can actually think about maybe releasing something to the community and getting it out there. So one of the very first things we did was, let's start simple. How can we get column-based data storage into the Spark as easy as possible? And so the answer to that was RDD. So RDDs really don't assume anything about the data. It's mostly just you have some object in an RDD, and Spark really doesn't care what that object is, and you just perform operations on that object. So what you could do is you could take something like Arrow, batch up your data, and put it into an RDD, and then kind of operate on top of that RDD. So in a sense, what you're doing here is you have RDD where each tuple in the RDD is actually a part of your table, so an Arrow batch. And this kind of is sort of interesting because now you get things like you can do zero copy between Scala side of the world or the JVM and Python because there's no more serialization. You can just use the Arrow to do direct access between the two different languages. And also, like, you're now in the column world, so we could take that data, move it to the GPU, and perform operations on it very quickly. But as you imagine, there's some really big problems with this. First of all is the whole Spark community and all the users are moving to the dataset and dataframe API, so introducing a new feature to the RDD API is a bit going backwards. But even worse than that is you're now in this world where you're operating on lots of little pandas tables. So you're sort of in this halfway world between row-based and column-based, and it works, and you can get things really fast, but it's a very awkward way to program. And because of that, like, you can't use normal Spark features because they all kind of assume rows. So when you have like sort of rows and sort of columns, things kind of fall apart pretty quickly. And the worst thing of all is, like, if we release this API and users wanted to do GPU operations, everything would have to be rewritten from scratch. Like, none of the current Spark code would be functional. And that's like not the correct way to go about doing this. So the question is, so we have data frames. People are moving towards data frames. They like it. And there's some like really nice features of data frames. So can we move to this column-based storage mechanism on the data frames and leverage some of like the Project Tungsten and some of like the code writing abilities of that API to kind of switch that model a bit to make that code just as fast as we were kind of seeing on the RDD side. And the real hope here is that there's little to no code changes for these jobs. They could maybe just a configuration setting, and now the data is columnar versus row-based. And of course, like now, because you're in the dataframe API, it's the same API that people are used to at this point. So kind of what that means is we kind of use the underlying mechanisms of Spark. So like there is already some column-based ability to read data in Parquet in Spark. And there's also, of course, Arrow support for the PySpark side of the world, so with the pandas UDF. So there's already some bits and pieces of this column-based processing going on in Spark. So can we leverage some of these bits and pieces to kind of push more of the entire like job into column-based format? And because of this, so if we can like make use of internal Spark code and the fact that it already does some column-based things, and we can make use of like the interpreter and like the planner to do this, hopefully users can just opt in with one configuration setting, and then they will switch from column to row-based without having to actually really rethink their job or how the job works. So we started there. So we started, okay, we can start to now like get deeper into Spark, change some of the operations from row-based to column-based. And now we can start to build on top of that. So that's kind of the first piece, again, those pieces into Spark. Then once you're there, like you can then start to think about moving the data to the GPU. So now that each operation is happening in column-based format, we're kind of staying in that format, you can push the data to the GPU, and like mentioned here, like start to like actually program some like the CSV parsing, hash join, and hash aggregates. And it becomes very easy to switch back and forth between either explicitly or with configuration settings. So this whole project is still in the very early stages, but so Ron was talking about a little bit about the mortgage data set, which is, we did some testing on, but it's very complex. But we also wanted to see, like, what kind of speed improvement can we get from this setup? So what this setup, so what just showing through is like a very simple setup where we had 31 million rows in a CSV. So actually sort of the same size as that mortgage data set. So can we read it from a CSV, do the group by, aggregate, and sum? And this is like showing like an 18x speed up between a 12-core single node cluster versus one V100 GPU. And so what's interesting here too is with the changes we made and the changes we're talking about is each one of those steps actually stayed in columnar. So when you actually do the CSV read, the CSV reads happening on a GPU. It's read into a like Arrow type format. Then when you do the group by and aggregate, it's staying in that same Arrow-based format to do each operation. So you're no longer, you change a little bit of the model where a lot of times Spark will try to read column-based, but will kind of read it from rows and kind of pass it through. This is trying to stay in column-based format and also trying to stay on the GPU as much as possible. Of course, when you have group bys, you have to shuffle, so there's going to be coming off the GPU and moving around. But the thought is to try to stay in columnar and try to like stay on the GPU as much as possible to make use of that speed and kind of reduce the overhead of going back and forth between the device and the host. And like I said before, this 18 speedup would just be no code changes. You would just go up and change one configuration setting, and it would go to this column-based format, and maybe another configuration setting to tell it to use the GPU. Another thing, so how this all works, though, is we didn't write the group by and sum. Last year, NVIDIA released a library called Rapids, which is easy way to describe it at a high level is pandas on the GPU. So you make a pandas-compatible API and move as many operations of pandas to the GPU as possible. So what we can do then is, since we have this pandas API, we can then connect to, once we're on the GPU, we can actually connect to Rapids and have Rapids do the operations for us. So this is actually kind of switching Spark to use column-based format, then also connecting to Rapids to kind of dump out and do the operations. So I want to say, like, very encouraging early results and rooms to improve, but we actually have like a ways to go. So a lot of stuff we've shown was kind of proof of concept and kind of figuring out if like this makes sense. And even like you never know before you start these projects if you're going to see a speed improvement. So will things become faster or slower, or will like the overhead of moving to GPU be too much? So we're at the point now where we want to reach out to the Spark community and ask questions about like, does this make sense to people? And can we break this apart and slowly get these things we've been working on into Spark itself? So the first one here is like, so before you can start any of that, right, like you have to have Spark aware of the GPU. So the first task here is to actually make Spark aware when it's scheduling the jobs that knows that the cluster has GPUs in it and knows how to use the GPUs. So that first Spark ticket is to make use of, makes the Spark schedule aware of GPUs. Then you have to go a step further and say, okay, each stage in Spark has to be aware of GPUs and accelerators. So we have to add that into Spark. Then a follow-on is like you also have to be in columnar to do these operations. So that's another change to Spark to switch to a columnar-based format. And the hope is like we can start to like reach out to community and say like we saw really big improvements with these things, and we hope that we could get there. And Ron, do you want to say a few things about like the improvements with the XGBoost, or like what you're thinking about?
Yeah, sure. XGBoost is similar, right? It's not kind of directly a Spark problem, but if you want to kind of train production models, you typically run XGBoost on Spark. So it's similar to what Rich said. If you're processing data in column format, it's much more suited to some of parallel processing, right? So that's the cuDF is a library in Rapids. It supports dataframe, but in columnar format. So we want to have that integrated into XGBoost, so you don't have to, reading your data maybe from Parquet is already column-based, and then you convert to rows, and then you convert to the batches and feed into GPU. There's a lot of data conversion that's going to be super slow. The other thing is right now a lot of algorithms assume you're going to fit everything into the GPU memory. So we're getting bigger and bigger GPUs. I think the T4 has 16 gig. There's like 32 gig versions coming out. But still, like if you have 10 terabytes of data, you're going to have a lot of you need a lot of GPUs to actually train on the full data set. So we're working on supporting sort of out-of-core external memory computation with XGBoost. So if you have your sort of data on disk, we can stream in the data in batches and still have reasonable performance. So these are all sort of in progress. I think that's the last we have. Oh, I finished pretty early. So we have plenty of time for questions. Anyone has questions?
Yeah, if you have a question, please go to the mic stand.
Hi. Yeah, so GPUs I'm aware of doesn't have the notion of cache, L1, L2, L3 caches. Cache, there is no cache in the GPU core, so how does Spark SQL work, because it leverages the notion of the caches and so the registers per se. So how does the compute work for things like vectors, vector computation, SIMD, loop unrolling, etc.?
Did you get the question?
Yeah, so I think, try to rephrase. So you asked about how would like Spark caching that normally happens on in memory or like on disk or something would happen on the GPU? Is that the question?
Spark SQL uses the notion of the registers.
Yep.
So, but GPUs don't have those kind of registers. So
yeah.
How Spark SQL scales with respect to when you do it on?
Yeah, so I guess the way to say that is there's still a very long road to go on this. So, and when you enable GPU, it doesn't mean you're not going to use the CPU. So the thought is over time, we'll move some operations to GPU, but keep other ones on the CPU. So, because there are some things you can imagine like being really good in the GPU, and it was also kind of like the first things to try, then like longer tail, we would figure out if it makes sense to move to the GPU and also, but still like leverage the CPU. So I think it's kind of, we don't know about all the features yet that could be done on the GPU and kind of get in there. Like there's even bigger questions too, like UDFs and stuff, which is a whole nother process of figuring out how that would work on the GPU.
Sure. So one other question is with respect to memory controllers between the RAM and the GPU. So if you have more cores on your Tesla, then how do they map back when the I/O happens? So predominantly, it is possible that there will be I/O bottleneck. Then the cores will be starving of the data. So
right. So if I understood the question, so if you look at the sort of a GPU architecture, right? It has a lot of cores. It has its own internal memory controller that connects to the GPU memory. Those are usually pretty high bandwidth. But connecting to the rest of the system to the CPU main memory is through PCIe. Usually that's not too fast. So traditionally, you see the most benefit if you have a very sort of a very dense compute, right? You copy some data and you do a lot of computation on that data. That's why if you look at deep learning convolutional networks, they just, you copy the image and the filter in, they're just kind of doing the sliding window, doing a lot of computation. So that's a perfect fit for GPUs. Once you go off that and you do other things, it sort of becomes sort of a more trade-off, right? If you say copy all the data over and you're doing like one pass, maybe the benefit is not that big, right? Even though you have sort of a very high memory bandwidth on the GPU, but there's this bottleneck between the sort of the host memory and the GPU memory. It's kind of I think there's also, we're trying to improve it on the hardware side. So this is PCIe is only on the Intel platform. If you use the IBM Power 9, they actually have the NVLink built into the CPU. The memory controller is in there. The NVLink controller is in the CPU itself. So you actually have very high bandwidth, very low latency connections. I don't know, maybe one day we'll also see that in other sort of platforms. But right now, it's sort of something you have to watch out for.
Yeah, so one last question, sorry. If you have a driver, Spark driver, which is multi-threaded, so how does the GPU computations work and how do they, did you have any test corresponding to that?
So a Spark driver, you said, or?
Yeah, Spark drivers are multi-threaded and Spark submitting multiple jobs in parallel. So how do they?
So
the same Spark session. So
yeah. So the hope is with the GPU scheduling is that like Spark will become aware of a GPU as a resource. So like when you submit a job and you start the job, like it would just get Spark will give like the job that many GPUs as necessary to run that workflow or that step or that task or wherever it is, or even that stage is to hopefully get to the point where each stage could be run and the GPU handed over to it.
Okay, I'm concerned with the task switching between in between a stage progression that happens when there are multiple tasks compete. So, have any performance test done on that, or?
We're starting to, like it says, very early stages, especially because we're still in the early stages. We even think about what it means to like be like the stages be aware of the scheduler. So there's many open questions.
Thank you.
In regards to that.
Yeah, so thank you, very good presentation. Yeah, I'm very positive to supporting the GPU on Apache Spark. So my question is, when GPU processing the data frame-based operation, so how do you write back the GPU result into the Apache Spark? I mean, so current Apache Arrow supports only read. The current Spark does not support write back to the result into the Apache Arrow.
Yeah, so I think the answer to that is like, I mentioned Arrow a little bit to the RDD side, but like when we went to the dataframe side.
In the RD, I'm talking about the data frame operation.
Yep, exactly, yeah. So we're not quite using Arrow at this point there. We're using the internal column base. So we have a slightly different version of the Arrow format that we're trying to stay very close to the format, but it's still an open question in those Jira tickets I mentioned is, if we make the column-based API public for users, should that be Arrow or should it be the kind of a slightly different API that's similar to Arrow? So what kind of saying there is we're not quite using Arrow, so we could kind of like write what we need out of the steps, so we could change it a little bit.
Okay.
So I'd like to ask the communication path between servers. Do you use the Spark side communication, or do you use any other communication path like MPI or some other communication path?
Are you asking if you use like just Spark or MPI or?
Yeah, well, my question is, what is the communication path between the servers? Right, so within multiple GPUs, you can use NCCL, but between the servers, you need to use the communication path but provided by Spark or some other communication path. So.
Right, so I can speak about the sort of the XGBoost side, right? The XGBoost is really just running on top of Spark. It's somewhat independent of Spark, right? Once you set up the XGBoost workers, they will just communicate between each other. There's sort of a handoff. Spark says, here's all the workers, go build this model. So for XGBoost, it's running on the GPU, we actually use Nico to communicate between the workers. For Spark itself,
I think still we're trying to stick as close to the Spark model as possible. So like shuffle and things will happen in Spark, and then data will be moved to the GPU when it gets to the worker. So the processing and the actual like computation happens in the worker, but the multi-GPU setup will happen across the network as like normal Spark shuffles.
Okay, thanks.
all right, thank you.